past few videos we were discussing about interference of light. So what is meant by interference? And interference, Young's double slit experiment and the condition for sustained interference, all those data we discussed. And today now we will discuss a new phenomenon known as diffraction of light. Okay. Diffraction of light. Diffraction of light means the bending of light around the obstacle, around the corners of obstacles, and the further encroachment of light into geometrical shadow is known as diffraction of light. Bending of light around the corners of small obstacles and the encroachment of light into geometrical shadow is known as diffraction. Now by this sentence you may be still more confused. So we will discuss what is meant by that in detail. Okay. So here if we are keeping an aperture or a thin slit and the source of light is kept here. And if we are keeping a screen, according to the rectilinear propagation of light, we know that this region should be, what is the specialty of this region? This will be completely bright, and above A and below B should be perfect darkness. No? Above A and below B should be perfect darkness because a small slit is kept. Okay. So through that only light is entering. So that light will be spread into this region. So we expect only AB region will be of bright region. But actually when we will do the experiment, when the scientists did the experiment or when they were performing the experiment, they could notice that not only AB region is bright, above A and below B, not perfectly bright, but it is not perfectly dark also. Some spreading of light was taking place. Okay. Alternate bright and dark fringes they could observe above and below B, similar to interference pattern. Okay. So it was not, geometrical shadow was not perfectly dark. And another one is that an obstacle is kept on the path of a source of light. A source of light is there. An obstacle is kept, and here a screen is kept. So here also what we could expect. So this region AB should be perfectly dark. AB region, because an obstacle is kept, it will not allow light to pass through this. So according to rectilinear propagation of light, we expect a perfect shadow of this object on the screen at AB. In between A and B, we will expect a perfect shadow. But what it was noticed is that AB is not perfectly dark. Here also some amount of light is reaching here. That is, the geometrical shadow is not perfectly dark. That phenomenon is known as diffraction. Why it happens? Because bending of light around corners. Light is bending. Because of that, it reaches or it comes to the corners of obstacle, and further encroachment of light into geometrical shadow. Further spreading of light into geometrical shadow is known as diffraction. This diffraction of sound is a common phenomenon. Bending of sound around the obstacles and those, it is a common phenomenon. But diffraction of light is very difficult to observe because for diffraction to take place, the size of the obstacle or size of the aperture should be comparable to the wavelength of light. In the case of sound, that is not an issue because sound wavelength is very large. But in the case of light, the wavelength is in the order of 10 raised to minus 10 meters or 10 raised to minus 9 meters. Wavelength is very small, because of which the bending or the diffraction is difficult to observe. Okay. Even though it is difficult to observe, we can observe in certain conditions if the size of the obstacle or size of the aperture is smaller comparable to the wavelength of light. In those situations, we can observe this diffraction. Okay, is it clear? And now we will discuss about diffraction at a single slit. Diffraction at a single slit. So here we are going to discuss about diffraction at a single slit. Okay. For that we are considering a slit. In the case of Young's double slit experiment, already we discussed, where we considered two slits. So instead of that, if only one slit was used, what happens? That only we are going to discuss. A single slit is there, and the slit width is A. Width of the slit is A. So let L and N, this point corresponds to L and this point corresponds to N. Okay. So here in diffraction, what happens is that here each point is acting as a source, and from each point waves are traveling, and those waves are superposing to produce diffraction pattern. In the case of interference pattern, two coherent sources. From those two coherent sources, light are traveling, they are superposing to form interference pattern. But in the case of diffraction, from the same slit, each point can be considered as a point source for the new disturbance, and from each point the waves are traveling. So those waves are superposing to produce diffraction. Okay, so we are considering the point P. That point whether to be bright or dark. For that, what we have to see, we have to find what is the path difference between the waves, and we have to find the condition for constructive, for how we can get maximum and minimum. So here we are considering we have to consider that point P, whether it is bright or dark. How to find that? So here from L and N waves are traveling. So those waves are superposing, and we have to find what is the path difference between the waves traveling from the point L and N. Okay, and let M is the exactly center point. Okay, that we will discuss later on. So we can consider M. M is the midpoint. So here, how to find the path difference? We can draw a perpendicular from here. And let the waves, this is the center point, to see waves traveling from these L, M, N points to the points. Okay, so this is there, and here we are considering a point P such that it makes an angle theta. Okay, it makes an angle theta. You can see that everywhere these are parallel, so we can see that to the point P, the line will be making an angle theta. Now we can connect these. So this is A. This angle you can mark it as LNQ. So we can write from triangle LNQ. If you are considering the triangle LNQ, angle LNQ can be written as 90 minus theta. because angle LQN is equal to 90 degree. Here we have drawn perpendicular LQ to NP. Okay, so this angle is 90 degree. This is theta. So we can write LNQ can be written as 90 minus theta. So angle LNQ is equal to theta. NLQ is equal to theta. Okay, NLQ is equal to theta and LNQ is equal to 90 minus theta. Okay, is it clear? Now what we have to find? We have to find the path difference. Path difference we can write it as path difference between the waves traveling from N and A. Path difference between the waves traveling from N and L to P. That we can find. How we can find? NP minus NP. So path difference we can write it as NP minus. Path difference we can write with small letter p. NP minus. So QP, from QP and LP that distance same because we have drawn perpendicular. So the extra distance travelled by the wave from N is NQ. So that is equal to. Okay. Now we can consider the triangle from triangle L and Q. From triangle L and Q. We can write NQ by Ln is equal to sin theta. NQ by Ln is equal to sin theta. NQ divided by Ln is the hypotenuse, that is equal to sin theta, or we can write NQ is equal to Ln into sin theta. NQ is equal to, what is Ln? Ln is the width of the solution. A is B. So we can write R difference is equal to A sin theta. So this is the path difference between the two waves which are separated by A. If the two points were separated by a distance y, we can write. If the two points were separated by a distance y, our difference can be written as y sin theta. Here the two points are separated by A, that's why we have written as A sin theta. If they are separated by y, we can write it as y sin theta. And we can see diffraction pattern, bending, or we can see bright and dark fringes only for certain small angles. So we can consider this can be approximately equal to y theta. And here also this can be approximately equal to A theta. By theta is small, you can write it. Theta is small. Here also you can mention theta is small. So the path difference we wrote it as y theta. Okay, path difference between the waves which are between the points. Path difference between the waves which are starting from 2 points separated by y is given by y theta. Okay. Now we have to find what is the condition to get the path difference to be, but the waves to be, crust should come together and either crust should come together or crust should come together. So that will be corresponding to maximum intensity. If one crust and one trough combines, it will be minimum intensity. So there is integral by using integral calculus one of a grid diagram that we are omitting here. And here we will discuss only that final expression and by taking the final expression and by keeping each condition, we can show that that is maximum or minimum. Okay. So we can write for theta equal to 0. When theta equal to 0, what happens? When theta is equal to 0, it is the central maximum. All path difference is equal to 0. Central maximum. Path difference is equal to 0. So maximum intensity will be there corresponding to C. Okay. Now other maximum and other minimum we can find. So the condition for minimum is given by condition for minimum is given by theta is equal to n lambda by A, and condition for maximum is given by theta is equal to n plus half lambda. In value varies from plus or minus 1, plus or minus 2, etc. Okay. Then plus or minus 1, plus or minus 2, etc. Here also n varies from plus or minus 1, plus or minus 2. So this is the condition for minima and maxima. Already we discussed here central point will be of maximum intensity because our difference is 0. So all the waves will be, either thrust will be reaching, that is from each point of the slit. Either waves are traveling, so those waves, either their thrust will be combining or trough will be combining to get maximum intensity. So central point will be of maximum intensity. Now condition for minima that you have to remember. Actually there is proof for that also, but not for your level. That's why we are not going to discuss that one. So you have to remember these two expressions. Condition for minimum intensity is given by theta is equal to n lambda by A, and condition for maximum intensity is given by theta is equal to n plus half lambda by A. Now we can check whether it is true or not. So first minimum where we will get, for first minimum, we can write theta is n is equal to 1. We can write theta is equal to lambda. So here what we are doing is that we can assume that slit is divided into two halves. Okay, two halves exactly. So that corresponding to each point in first half, there will be a point in second half, so that their path difference is equal to A by 2. Assume the slit to be divided into two halves. Assume the slit is divided into two halves corresponding to each point in first half. Corresponding to each point in first half. There is a point in second half. So that the path difference is equal to or the separate, so that the separation of path difference, the separation between the points is equal to, so that the path difference of separation. So that the separation between the points is equal to. Okay, which means here if we are considering that slit, we are dividing it into two halves. So if one point here we are considering, another point we can consider here, so that their separation is equal to A by 2. Similarly, one point here we can consider, correspondingly another point here we can consider A by 2. that's why corresponding to each point in first half, there will be a corresponding point in second half, so that the distance between the points will be A1. Okay. So now we can find what is the path difference. Path difference can be found out as path difference is equal to y theta. So instead of y, we can write A by 2, and theta corresponds to first minimum lambda by a. So what we got? Path difference is equal to lambda by 2. So what it means? Path difference is lambda by 2. Means phase difference is pi, which means that one crest and one trough will be superposing to have minimum intensity. Okay. Path difference, if it comes lambda by 2, what it shows? One crest and one trough will be reaching that point P where theta is equal to lambda by a. Whichever point satisfies this condition, that will be of minimum intensity. Lambda by a, then 3 lambda by a, then 5 lambda by a, all those points will be of minimum intensity, because for all those we can say that path difference will be lambda by 2 or phase difference is pi. So this is the condition for minimum. Okay. So even though we are writing this is general expression, we can show each will be true. For first minimum we have shown like this. Okay. Similarly we can show that first maximum whether it is true or not. Okay. Is it clear? Understood? Now we will discuss about the maximum. Now for first maximum. First maximum means other than the central maximum, or we can say the secondary maximum. Okay. Other than central maximum, the next maximum. Okay. So that corresponds to n is equal to 1. Now if you are substituting n is equal to 1, which means theta is equal to 3 lambda by 2. If you are substituting n is equal to 1 in this expression, 1 plus 1 by 2, you will get it as 3 by 2. So 3 by 2 lambda by a is the condition for first maximum other than central maximum. Now we can check for whether this is maximum point or not. How we can show? Here we can assume that slit is divided into 3 parts. It was slit is there. We can assume that divided into 3 parts. A by 3, A by 3, and by 3. Okay. Corresponding to each point in the first 1 by 3, there will be a corresponding point in the next 1 by 3, so that their separation will be 1 by 3. No. Similarly, corresponding to next, here also we can assume another one, so that their separation is equal to 1 by 3 or A by 3. No. So corresponding to, we can assume that slit is divided into 3 parts. And 2/3 part, if we are considering, corresponding to each point in the first 1/3, there will be a corresponding point in the second 1/3 also. So that their separation or their distance will be equal to A by 3. Okay. So path difference is equal to what you can write y into theta. Here y is A by 3 into 3 lambda by 2a. What you will get? Which means 2/3 slits contribution get cancelled. 2/3 slits contribution get cancelled. Why they are cancelling? Because from 2/3 slit, the part we can consider each point in 1/3 of the slit, corresponding 1/3 in the next 2/3 slit, so that their separation is equal to A by 3. So that path difference is equal to lambda by 2. So their contribution will be cancelling, because for them crust of either one crust and trough will be combined. Okay. Then what else left? Only 1/3 slits contribution. Okay. So only 1/3 slits A by 3 1/3 1/3 slits contribution will be there. Okay. At the point P, only 1/3 of the intensity will be there. Similarly, next what happens? 1/3 of the intensity, no? 1/3 the waves traveling from this slit. That only will be contribution. Next, if you are considering it as 5 lambda by 2a, we can divide that slit into 5 parts. 4 parts contribution will be cancelled, then only 1/5 contribution will be. Next, we can assume next maximum 7. We can divide it to 7 parts. 6 parts contribution will be cancelled, only 1/7 of the waves traveling from that part will be contributed. So we can say that in the case of diffraction, intensity will be gradually decreasing. Okay, intensity central maximum will be maximum, and as it goes to secondary maximas, intensity gradually decreases. Okay, now we can plot the intensity distribution curve. The intensity distribution curve. Here we are talking a graph between intensity and angle. Here we are talking a graph between intensity versus angle. So central maximum will be of maximum intensity that already we discussed. Minimum corresponds to first minimum lambda by a. Here we can write minus lambda by a. Next minimum 3 lambda by a, no, in lambda by a, 2 lambda by a, 3 lambda by a, and so on. Because minimum corresponds to beta is equal to n lambda by a. The intensity gradually decreases. We can see that here intensity gradually decreases. The intensity of the secondary maxima, first secondary maxima will be only 4% of the maximum intensity. Okay, it will go in the ratio 1:21:21:1/61:1/21. So okay, so here it will be only 4% of the first maximum. So this is the main here this point minimum 2 lambda by a. This is 3 lambda by a, and here we can write it as minus 2 lambda by a, minus 3 lambda by a, and so on. So here you can see that intensity gradually decreases. In the case of interference, you may be remembering in case of or whether the central maximum or first maximum or second maximum, not a matter, all are having equal intensity. But here you can see that intensity gradually decreases. Okay, so this is the intensity distribution curve. There we plotted intensity versus linear separation x, but here we are plotting intensity versus angular separation. Not a matter. Here you can see that intensity gradually decreases with the angle. Okay, is it clear? And now we will discuss about the angular width of central maximum and secondary maximum. All those we will discuss. Okay. So here we are going to find out the width of central and secondary maximum. Okay. So already we discussed if a slit of width a, if it is illuminated with light, theta is equal to n lambda by a is the condition for minimum intensity. So here we are considering a slit of width d. So what is the condition? Theta is equal to first minimum occurs at an angle, this angle, when theta is equal to lambda by d. And here when theta is equal to lambda by d. So these points corresponds to first minimum. So angular width of central maximum we can write angular width of central maximum two into theta, which is equal to 2 into lambda by The angular width of central maximum is given by 2 lambda by d. Why? Because this here first minimum occurs and here corresponds to first minimum. So up to that central maximum will be there. So angular width of the central maximum is equal to 2 lambda by d. Now we can find what is the linear width. Linear width of central maximum is equal to 2 lambda d by d. How we are getting? We can write angle is equal to arc by radius. Angle is equal to arc length divided by radius. Arc length angle is equal to 2 theta, which is equal to arc length is given by what is that? Fringe width, linear width, fringe width beta divided by radius is. Okay, so linear width or beta of the central maximum is given by 2 lambda d. Okay, linear width. Is it clear? Next, this is for central maximum. Now we can find what is the angular width of other maximum. Angular width of other secondary maximum. How to find? We know the condition. Theta is equal to n lambda by a corresponds to minimum intensity. No, minimum intensity. So theta is equal to n lambda by a, and next adjacent to that n minus 1 lambda by a will be there. So if you find the difference, you will get the angular width of secondary maximum. So this theta equal to n lambda by a minus n minus 1 lambda by a, and that is equal to, sorry, not a, here we have considered the width of the slit as d, so we will get it as n lambda by d minus, here we consider it as n minus 1 lambda by d, so that we will get it as So you can see that angular width of other maxima is only lambda by d, but angular width of central maxima is 2 lambda by d. So we can say that angular width of central maximum is 2 times the maxima of the angular width of other secondary maxima. Similarly, linear width you can find. Linear width of other secondary maximum is equal to lambda into capital D by d. So here also you can see that in the case of interference, all fringes are of equal width, but here you can see that central fringe will be of 2 times the width of other fringes. Remaining all other fringes are having width equal to lambda d by d, but central fringe has a width of 2 lambda d by d. Okay, is it clear? So today we discussed about what is meant by diffraction and diffraction due to a single slit, and we discussed the intensity distribution curve in diffraction and the condition for, or what is the expression for the angular width and linear width at central maximum and other secondary maximum. Okay, is it clear? I hope all of you understood.